All right, so in our last section, we started looking at how to approach finding solutions of a first order differential equation of this form. And we talked about what that meant, basically that the function on the right hand side, f of x and y, is just an expression that just involves x's and y's. And we said we took a kind of a general approach to this, and functions in this form, differential equations in this form, we can at least get a kind of a qualitative idea about their solutions by graphing their slope field. All right, and we can kind of see where the curves will go and how the curves need to flow and where the curves will end up. But again, we didn't actually find the solutions, we just kind of saw solution curves, kind of. So we want to actually start the process of solving a differential equation that looks like this. Now we're going to add one caveat. So this first set of differential equations that we can solve look like this, but what we need, we're going to focus on the situation where the function f of x and y can be written as a function of x times a function of y. So in other words, we can kind of separate it into two factors. This approach only works if that is possible. All right, so if you can break your function f down into an x factor times a y factor, then we can try separation of variables. And separation of variables is really the baseline for solving general differential equations. It's the first thing you try. You see if you can solve it. You solve these systems using separation of variables. All right, so let's look at a simple example. We will look at an initial value problem that looks like this. And of course, when you're solving an initial value problem, you first actually just find the general solution. You first just solve this, right? And so you get the general solution. And then, because there's an initial condition, you go on and find the particular solution. But we do find the initial solution, or the general solution, to begin with, which is kind of nice because we'll pair that with the slope fields and kind of see how that all works together. All right, so if we look at our f of x, y, we notice that we can break it up into two pieces, right? Just like is required. We can break it up into a function of x times a function of y, right? So we can kind of separate those into two factors. And it doesn't matter where we put the -6. If we put it with the x or the y, it does not matter. All right, so because we can do that, we can solve this using separation of variables. So the way this works is it kind of, the title of it tells you what you're going to do. You want to separate the x's from the y's. You want to get all of the x terms, including the dx on one side, and all of the y terms, including the dy, on the other side. Right? So get all the x terms on one side, get all the y terms on the other side, and that's your first step. So to do that, this y, let's just pencil this y will multiply across, right? We'll just kind of do it in steps so I don't make any mistakes. So it's y dy over dx. Let's do this. Dy, let me try it again. We divide it across, so it becomes 1 over y dy dx equals -6x. Now this piece, it's important to remember, we can split it up into the dx and the dy, so we can multiply both sides by dx, right? We'll just add all the details this time around, but so the dx's cancel and we're left with dy over y equals -6x dx. So you see we've separated the variables. All right. So if you can do that, then you have some hope that this method will work, because your next step is simply to integrate both sides. Okay, you're going to integrate both sides, right? I mean, we're following the rules of equations, which is whatever we do to one side of an equation, as long as we do the same thing to the other side, we haven't broken any rules. And so we're just going to integrate both sides. And here's where the system, the method either works or doesn't. You've got to be able to perform these integrations. In this case, we can do that. So we can integrate dy over y to be ln of y. Now technically it's absolute value of y, right? But we make some general and helpful assumptions that we're just dealing with, well, pretty soon we'll be dealing with just positive values. And if we have the right initial conditions, we won't have to worry about that absolute value. But for now, we'll put it in there, right? The integral of dy over y is ln of y, and the integral of the negative 6x is just negative 3x squared plus c. Now you might be saying, why didn't I add a c over here to the left side? I could have, but then I would have just brought it over and combined it with this c to get a brand new constant. So why not just create one constant there to begin with? Okay, and so it looks like we are really close to solving the system, or the differential equation. It's at this point, you know, ideally we would love to get y equals y of x, some expression, y equals some expression of x. In other words, we would like to be able to solve this for y to get what we call an explicit solution, and in this case we can. All right, so to do that we would just exponentiate both sides, right? So you get e, raise, or take e and use the left hand side as a power, as an exponent on e, and the right hand side as an exponent on e, and that leads us to this right here. The absolute value of y equals e to the negative 3x squared plus c. Now watch some of the algebra here. This right hand side I can write like this, right? Because if I've added exponents, I can actually rewrite it as a product, right? Most often we start with this and go to this, but we're just tearing them apart. What's important about this is that this piece, c is just a constant, so e to the c is just a constant. So I can just rewrite that individual term as c sub 1 e to the negative 3x squared. Notice I called it another constant just so we weren't confused. C sub 1. Okay, so I'm left with the solution absolute value of y equals c sub 1 e to the negative 3x squared. Alright, so we have this explicit solution. It's nearly explicit once we deal with that absolute value. Let's take a look at the slope field for this particular differential equation. So I've already typed it into GeoGebra here, and so you can see our slope and you can kind of imagine our curves going up. And one of the things that this slope field is helpful for is remembering, is helping us understand how to deal with the absolute value, at least in this case, because our initial condition is we need the solution that goes through the point 0, 7. So if we look up here at 0, 7, we see that the solutions, let's move this, let's bump this up a little bit. We'll run from minus 10 to 10. All right, so if we look up here at 7, 0, 7, we see that the curves, the solution curves, are going to be positive. So the absolute value is going to be positive. So that allows us just to drop our absolute value sign here and just deal with the curve y equals c sub 1 e to the minus 3x squared. That's going to be our solution curve. We don't have to worry about the absolute value. Now, just be aware that absolute value, sometimes we just kind of play fast and loose with it a little bit, and sometimes we'll just not put that in when we integrate dy over y. And by the way, you're very often, that's a very common integral. But to finish this off and to find the particular solution, we get, oh, let's do one other thing. Let's just look at, before we move away from this, these are our general solutions. So in GeoGebra we can see them here, right? And so each time I move this slider I get a different solution, so a different curve, right? And so those are my solutions. If my initial condition was negative, then I would have one of these as my solutions. One of those as my curves, right? But ours is going to be up here somewhere about, it'll be a little higher here. My slider doesn't go that way. But you can see the whole family of general solutions. Those are the solutions to the differential equation. Now, which particular one is the one we want? We want the one that goes through 0, 7 way up there. And so let's figure out which one that one is. And so we just do that using our regular approach. We say, okay, when x is 0, y should be 7. And so we see, oh, this is 7 equals c times 1, c sub 1 times 1. So c sub 1 needs to equal just 7. So y equals c sub 1 e to the negative, oops, we've got our solution. 7 e to the negative 3x squared is our particular solution. That's the solution to the initial value problem. And so if we graph that, we see that it fits just perfectly. There it is, the purple one. We see that it fits just perfectly into that family of curves. All right. And so we can even bump that up a little bit. There's our particular solution. All right. So you can see that solving by separation of variables is a very powerful way to deal with more complicated equations, differential equations. So let's try another one here. Grab my right pin. dy dx equals 4 minus 2x over 3y squared minus 5. Now remember the requirement. Well, let's just kind of walk through this process. Let's just take a look at the slope curves, or the slope field of this. So we'll jump over to Desmos, or to GeoGebra. Now, like I say, Desmos has this capability. GeoGebra, once you get a hold of it, once you get used to it, it's way more powerful. So if you want to start with Desmos, that's fine, but I would encourage you to jump into GeoGebra and learn how to use it. So here's the slope field for this, and you can kind of, if you kind of let your eyes unfocus, you can kind of see the curves, and they're kind of interesting because it looks like there's kind of like this little vortex here that they all circle around. So this is what the differential equations got to look like, or produce curves like, to solve this thing. All right, so let's see if we can take a look at solving it, take a stab at it. Now remember, let's walk through our thinking. First order, in other words, first derivative of y, and then this right hand side only contains x's and y's. Now it's okay that it has a y squared in it, that's all right, as long as it doesn't have any other derivatives of y's. That's what we're looking for. Now the next phase is it possible for us to write this right hand side as a product of an f function, 4 minus 2x, and a y function? And in this case it is. We can separate that into the x factor and the y factor. So again, the reason we do that is because that allows us to try to solve this by separation of variables. So let's move all the y terms together. So that amounts to needing to move this to the left side with that. So we can just simply multiply both sides by 3y squared minus 5. And then this gets moved up to the right hand side. So it actually is pretty simple in this case. 3y squared minus 5 dy equals 4 minus 2x dx. Right? And you see now we've got all the y stuff on one side, we've got all the x stuff on the other side, and so now we try to integrate. If we can integrate, then we're good to go. We're going to integrate the left side with respect to y and the right side with respect to x. So when we do that, we end up getting, let's see, the derivative of 3y squared is of course y cubed minus 5y. I don't put the plus c here because I'm just going to move it over and join it with the c from the right hand side, and then this becomes 4x minus x squared, and then I put my plus c. Now I do have to have a plus c somewhere, but I don't need two of them, so I'll just join them together, and there it is. Now here we have a solution, and this is what we refer to as an implicit solution, meaning there is no way I'm going to be able to solve this and get it in the form y equals some function of x. In other words, I'm not going to be able to solve for y because there's y cubes and y's. That's okay. It still represents a solution, a general solution to my differential equation. All right. So let's take a look. Let's take a look at the family of curves that this produces. So to do that, we'll just type this function into GeoGebra with the c, and when you put the c in, you get a slider, okay, and that lets you, but you can see that lets you select different values of c to graph. So here we are, various different values for the slider create all these wonderful curves for us. And you can see that they fit that slope field. Now notice that you even get this point at which that you separate into two curves for negative. There's c equals 0. Actually it starts even a little bit before that. But yeah, so those are your solution curves. They exist and we've able to find them, but we're just not able to express the solution as an explicit function, y equals some explicit function of x. But that's okay. We're just fine with that. So this is your first method for solving differential equations using separation of variables. It's the first thing you always try when you come up to a differential equation.